Hey guys, today we're going to do is we're going to talk a little bit about the rules of enthalpy. There's, I guess, three big rules that I want to unpack. We're also going to spend a little bit of time explaining what enthalpy is. We were talking a little bit about it last time, but I really want to unpack it a little bit more. In order to do that, we're going to need to jump onto another Paint documenty thing. Coo. Maybe I should just start by sharing my screen. I don't know. I'll have to figure out how to do that later on. Once I get more technologically savvy, I suppose. Okay. So let's make sure I got it. There we go. All righty. Okay. All right. So where's the last thing we talked about? We talked a little bit about we introduced this concept of enthalpy as being a state function of state functions. We had H, which means enthalpy, and then we had E, which stands for internal energy, and then we have P and V, which stands for pressure and volume, respectively. So our enthalpy is equal to our internal energy plus our pressure times our volume. Each one of these is state functions, and by that, we mean that basically a couple of things. Basically, we mean that we are really obsessed with the change of the state function, right? So it's always a delta state function, and that can be oftentimes reduced to the state function final. Make that smaller. State function final minus state function, not that small, minus state function initial. There we go. Okay, so we have this delta, this change in the state function, which is equal to the state function final versus or minus the state function initial. That's what we really like when we're talking about state functions. And each one of these guys, E, P, and V, these are all state functions. So enthalpy is a state function of state functions. Now, there's a couple things I want to highlight here that really clarify what enthalpy is. Recall that we have a couple other equations that we've been working with. One is focused on internal energy, which is delta E is equal to Q plus W, right? Q in this case means heat transfer. And then W means work. Okay. The other equation that we've been working with is work is equal to minus P times V. Okay. Importantly, the converse is true as well. That means that minus work is equal to plus P times V. Okay. So let's do a little bit of logic here. Let's say that we had a constant pressure. If we had a constant pressure, that would mean then if the pressure is constant, that would mean that the delta H, right, would have to equal the delta in internal energy plus P times V, right? Now, if we have the constant pressure, right, if there's no change in the pressure, right, we can just leave the pressure as is and distribute that delta with the E and the V. So that means that constant pressure, delta H is equal to delta E plus P times delta V. Okay. Now this is all very well and good. Now what we can start to do is we can start plugging in some of these other equations. Recall that our delta E is equal to Q plus W. Okay, that's from this guy up here, Q plus W. And as we said a second ago, plus P times delta V, I'm sorry, this should be delta V, excuse me, plus P times delta V is equal to minus work. So this guy right here actually equals minus W. All right, so if we swap that out, we end up with something like this. And now you're like, well, wait a second, Dr. K. There's a plus W and a minus W. So does that mean, yes, that's right. That means that delta H at a constant pressure is equal to Q. What that means then is that the change of enthalpy is equal to the heat transfer. Okay. So when we're talking about changes in enthalpy, right, that means that we're talking about how much a system has either released or absorbed energy, right? If we draw up a little diagram here, and if I have a system that I'm focused on and I have some surroundings with it, that system can either be transferring heat out or it can be absorbing heat, right? In this case, this would be a minus Q and this would be a plus Q, right? And importantly, that Q, right, is also the change of enthalpy. Now, a similar type of rule applies here as well. So if I have a minus Q, that means that I have a minus delta H, right? A minus delta H and a minus Q, that means that heat is released. This is what we would call an exothermic reaction. So an exothermic reaction is one where we're releasing heat. That means that we have a minus delta H and we have a minus Q. I'm going to say it one more time. An exothermic reaction is one that releases heat. That corresponds to a minus delta H and a minus Q. Plus Q, on the other hand, means that there's a positive delta H. This is something that absorbs heat. So it's the opposite of the other one. Okay. This would be what's called an endothermic reaction. Okay. So this is where we get our terms exo and endothermic. An exothermic reaction is one with a minus delta H that releases heat. A endothermic reaction is one with a plus delta H that absorbs heat. Okay, so that's what change of enthalpy is talking about when we're talking about change of enthalpy. We're talking about, all right, is this system releasing heat? Is it absorbing heat? And based off of that, we can learn, actually, as we'll learn later on when we talk about calorimetry, we'll learn some stuff about how we can learn stuff about the system using change of enthalpy. Now, there are a couple of big rules associated with enthalpy. Our first rule states that the change of enthalpy, so the change in heat content, is contingent on reactant used. Contingent on reactant use. What does this mean? So let's put this together in an actual chemical equation. Let's say I have, or actually maybe let's do an analogy first for the purposes of our purposes, right? So let's say that I have a log, right? And I toss that log onto a fire and the fire's burning. It's actually a pretty good fire. Well, never mind. That's a terrible fire. If I burn this entire log, right, I'm going to release a certain amount of energy, right? I burn the whole log. I got a certain amount of energy out of it, right? But now let's say that instead of just one log, yes, I put a second log on. Maybe even a third. Mayhaps a fourth, but let's just do three because I can't draw anything more complicated than that. Let's say I put 3 logs on and I make a big old conflagration from this, right? The amount of heat that I'm releasing from these 3 logs is going to be a lot more than the heat that I release from just burning the 1 log, right? The reason why is that the reactants used, there's way more reactants being used. There's way more logs being used. Similar type of principle happens when we're talking about changes in enthalpy. So the change of enthalpy is contingent on how much reactant is being used. If I have a combustion of methane, looks like an E. Let's see, balance this as I go. CO2 plus 2H2O. Okay, if I do this reaction, right, and I plug, I don't know, 5 grams of methane in, right? That's going to give me some amount of change of enthalpy, right? But if I put in like 30 grams, right, that'll scale upward, right? Whatever the change of enthalpy, I'm going to make up a number here. Let's say that it was 100 joules worth, right? Minus 100 joules, right? If giving me 5 grams of methane releases 100 joules, then that means that giving me 30 grams of methane is going to give me a higher number than this, right? Because more methane is being combusted, right? So the change of enthalpy is contingent on a reactant used. Now, this seems pretty intuitive, right? What this does do is it clicks into utilizing moles, right? So what does that mean? How do we connect these things? Okay. So let's say, actually, let me give us a good number here because I think I know this one by heart, actually. Minus 890 kilojoules per mole. Okay. All right. So let's say that if I do this chemical reaction, where's my pen? There it is. If I do this chemical reaction, and I know that every single time that I combust 1 mole of methane, I release 890 kilojoules of energy, right? I can ask a question like this. It'd be something like, let's say that I have 50 grams of methane. What is the change of enthalpy? Okay. Now, the way I would approach this problem is I have to, first of all, look at this guy right here. So our change of enthalpy usually is being given to us in terms of like kilojoules per mole or joules per mole, right? In this case, we know that every single time I combust 1 mole of methane, every time I combust 1 mole of methane, I'm releasing 890 kilojoules, okay? So what I have to do, let's make a protocol here. This seems like a good opportunity for a protocol. Let's put a raw her. Okay. So how to solve for change of enthalpy with grams of product, grams of reactant. Excuse me. Silly me. Silly Dr. K mixing up his words and such. Okay. So the first thing that we got to do is figure out change of enthalpy for 1 mole of reactant used. Okay, now this is given to us here. We have the minus 890 kilojoules per mole. So that means that when I combust 1 mole of CH4, that means I'm releasing 890 kilojoules per mole. Our next step is convert grams of reactant to moles of reactant using, yeah, you guessed it, mole equals to grams divided by molecular mass. This should be totally seamless at this point. You should absolutely be able to convert from grams to moles and vice versa. Once you have grams, once you've converted grams to moles, then you'll know how many moles you actually have. So our last step is to multiply moles by change of enthalpy. Report last number. Okay, because with this third step, what it's going to do is it's going to essentially, if we go back to our analogy here of like the fire, right? Step 3 here is going to tell you essentially how, or step 2 and 3, I guess, is going to tell you how many logs you have, right? And based off of how many logs you have, then you can predict how much flame you're going to get, how much energy you're going to get. Okay, so let's do this step by step. First things first, figure out our change of enthalpy for 1 mole of reactant used. We have 1 mole here, and that's 890 kilojoules per mole. That's great. So next thing we got to do is we got to convert. Let me do a little check mark because it's fun to do a check mark. Number 2, we're going to convert grams of reactant to moles of reactant, right? Using moles equals grams over molar mass. We're looking for moles here, so we'll do 50 grams divided by the molecular mass of the molecular mass of methane, which is 12 plus 4, which is 16. If I do that math real quick, that should give me 50 divided by 16. This should be 3.125. Okay. Real quick. Sorry, guys. All right, cool. Oops. Now it's freaking out. Okay, cool. So that's the amount of moles of methane that we have. Once we know how many moles of methane we have, right, and we know that that's the amount that's getting combusted, right, we multiply this guy by our minus 890 times minus 890. That gives me it's a big number. 2781.25 kilojoules. Notice that we had moles up here, and then our enthalpy was kilojoules per mole, so we cancel the moles, and we're left with kilojoules. So that tells me, right, if I have 50 grams of methane, and I know that I'm releasing 890 kilojoules for every mole of methane combusted, this is how I can connect this with things like grams of reactant, okay? So first things first, to solve for a change of enthalpy, given a gram of reactant, you're going to figure out what the change of enthalpy for 1 mole of reactant is being used. That's typically given. Secondly, you're going to convert grams of the reactant to moles of the reactant using moles equals grams over molar mass. Then what you're going to do is you're going to multiply moles by change of the enthalpy. And then that's going to give you your final change of enthalpy given the reaction parameters, excuse me. Okay. So that's rule number 1. The change of enthalpy is contingent on the amount of reactant used, right? If you have a lot of a reactant, you're going to have a lot of change of enthalpy. If you have just a tiny amount of the reactant, then you're going to have a small change of enthalpy. Next, I guess, it's also pretty intuitive. But rule number 2 states, you know what? It's ridiculous. I'm just going to type it out. We have the technology. So rule number 2 states, the change of enthalpy is equal in number, but opposite in sign to the reverse reaction. Okay, what does this mean? So the delta H is equal in number but opposite in sign of the reverse reaction. So I think this one also is pretty intuitive if you just explain it a little bit, right? Let's say that I have a reaction that goes from A to B. Okay, let's say I'm going to make up a number here. Let's say this releases 100 joules of energy. Now let's say I'm like, okay, I'm sick of B. I want to go back to A. I go from B back to A. This equation, number 2, is the exact same equation as number 1, right? It's just reversed. But since doing equation 1 releases energy, then doing equation 1 in reverse should absorb energy, right? And it's not just a random made up number. We have the exact same molecules involved, A and B, right? So we're just literally reversing the first reaction. So the amount has to be the same as well, right? So this is where we get the idea that the change of enthalpy of a reaction, right, is the exact same number, but has an opposite sign of doing the reverse reaction. So let's go back to our previous one on combustion of methane. Let's say that I have CH4. We said a second ago, let's say this releases 890 kilojoules per mole of methane, right? Okay. Now let's say that we want to know how much the synthesis of methane would be, the reverse of the combustion of methane, right? If I do this reaction in reverse, CO2 plus 2H2O, so on and so forth, it's the exact same reaction. It's just flipped. It's just now the reactants have become the products and vice versa. It's the exact same reaction. And so that means then that similar type of principle, exact same number, but with a flipped sign. Okay, so combustion of methane releases 890 kilojoules per mole. Synthesis of methane is going to absorb 890 kilojoules per mole. Okay, so that's our second rule. The change of enthalpy is equal in number but opposite in sign. This is going to show up again when we start talking about something called Hess's law, which I'll do another video on later on. But that's let's address that first rule first. Okay, the last big rule has to do with phase of matter. So rule number 3. The delta H depends on the phase of matter. What does that mean? There's a couple different things I want to talk about here with this one. One is a little bit more intuitive. The other one, you just need to get over like a conceptual hump. We'll talk about that in a second. But the delta H depends on the phase of matter. So what does that mean? That just means a couple different things. It means that first things first, First things first, it means that, let's say I do a chemical reaction. Where's my pen? There we go. Let's say I do a chemical reaction. Let's say I have A, and that's a gas. And that gets converted into B, which is also a gas. Okay. And let's say that it has some change of enthalpy associated with it. Let's make up a number, 100 joules. Okay. Now, let's say I cooled these things and turned them into liquids. The A liquid and the B liquid. Okay. Just because it's the same molecule or the same atom, right, in the same chemical reaction, right, doesn't mean that it's always going to have the same change of enthalpy, right? Because in this case, because they're in liquid form as opposed to gas form, the change of enthalpy could be something totally different. Let's just say some other thing. All right. And that's what we're talking about when we're talking about the third rule. The change of enthalpy depends on the phase of matter. If A and B are both gas, right, they'll have some known enthalpy change associated with it, right? But if A and B are liquid, even though they're the same molecule, because they're in different states, that impacts the overall change of enthalpy. Okay, so that's the first thing. The change of enthalpy depends on the phase of matter. It's worth talking here about how about energy changes for systems as they transition from one phase of matter to another. So let's say I have a solid mass. Let's call it A. Right? It's a solid, and it changes into a liquid. A. So in this case, you could ask this question like, okay, is this absorbing energy or is this releasing energy in order to do this reaction? The answer here, you have to think about like how the individual atoms or molecules are moving, right? In this case, the atoms are really, really close together. And they're vibrating, but they don't have a ton of energy. Okay. In this case, they're moving around a little bit more. They don't have a defined volume, or they do have a defined volume, but they don't have a defined shape, right? They are moving around a little bit more. Okay. So the transition for A to go from solid to liquid requires an input of energy, positive delta H. Okay. Similar type of thing. Any transition from solid to liquid, from solid to gas, from liquid to gas, all of these require input of energy plus delta H. Okay. On the flip side, anytime we're going from a more disordered, you can kind of think about it that way, a more disordered form of matter to a more ordered form of matter. So like if I'm going from gas to liquid, from gas to solid, from liquid to solid, right? All of these are going to require the atoms or the molecules to not be moving around as much, right? So they need to be losing energy, right? So each of these is going to result in a loss of energy. Okay, it's a little counterintuitive at first, but if you just think about what's happening to the molecules in a given phase of matter, then that explains it a little bit better. Okay, so those are the three big rules that I wanted you guys to pick up. The first one, delta H is contingent on the reactant used. We did a little protocol to relate grams of a reactant to overall change in enthalpy. Rule number 2, the change of enthalpy is equal in number, but opposite in sign of the reverse reaction. So if I go from A to B and that releases energy, then going from B to C has to absorb energy in the same degree. And then finally, rule number 3, the change of enthalpy depends on the phase of matter, right? So just because I convert from A to B in gas form doesn't mean that converting from A to B in liquid form leads to the same change of enthalpy. And we also talked here at the end about how transitions from one phase of matter to another, how we can infer whether or not they're taking in energy or releasing energy. This is all couched within a overall broader conversation as to what enthalpy is. I'm going to go ahead and stop right there because the next concept, Hess's law, is also kind of a difficult concept, or some folks find it difficult. But either way, I'll drop this now and then we'll do another video on Hess's law later on. But anyway, guys, that's all I have for you today. K-Money out.